Hi, everybody. This is Marco Bertoni on demand flexibility and grid interactive efficient buildings. I'm a scientist at Berkeley Lab, and I will give you a short introduction on demand flexibility, and then I'll pass it to Jingjing Liu and Cindy Renier, who are going to present you two large projects around grid efficiency, grid interactive efficient buildings, funded by the Department of Energy and the California Energy Commission that show some very interesting kind of bleeding edge and cutting edge technology. So I want to be very brief, so I'm getting directly to the conclusions. Are green interactive buildings a reality? The answer is yes. Somebody just wrote that is actually a movie, and so it's not really reality. And so we'll have to get a little bit deeper than that to understand if efficient buildings are reality or science fiction. So I want to start with the very long and tedious description of what GAB technology is and see if we can agree on what it is. Grid interactive efficient buildings. GAB is energy efficient building that uses smart end-use equipment and other on-site DR to provide demand flexibility while co-optimizing for energy cost, grid services, and occupant needs and preferences in a continuous and integrated way. So these buildings are supposed to be efficient, connected, smart, and flexible. So I have done several projects in real buildings, as I think you are familiar with them. And I kind of imagine what you're thinking. Buildings are really efficient, so you can see persistent low energy use that minimizes demand, as you can see from the picture, realized in practice nowadays. They're also connected, the kind of state-of-art connectivity there, communication, two-way communication. There's a phone, so it's two-way. It is flexible with a pneumatic system on the right. That's very flexible to change. And you can see also the response to occupant needs on the bottom. Buildings can also be very smart. This is actually pictures from a system that is currently running at LBNL in one of our buildings, from a company that went defunct in the 1990s and left us with the MS-DOS-based control system that is, as you can see, very innovative and smart. And these are some of the peripherals and other elements that we have in a building that is maybe an exception, but not that much. And I believe you probably have seen some of those. And flexible, buildings should be flexible. So I actually picked a figure that should really describe well the concept of flexibility. So back to us, I think that my revised conclusion based on the information provided is that buildings are not really GAB, and they're not real. As you can see, that building is not efficient. Well, it is efficient because it has no energy, but it is not connected. It is not very smart, and it's kind of falling apart. So I think that that's as unfair as my first statement. So we should really reflect on what GAB is on a practical term, because we're going to see in the next two presentations, implementation of GAB. And I want to make sure that you realize that this is not something completely alien. So if you reread the sentence that we had read before, the definition of GAB, in terms of its main components, GAB is basically energy efficiency plus demand flexibility. And honestly, we have been doing demand energy efficiency for years. Many of the people on the call are expert in this area. And we have been doing it with hardware retrofits, with controls, and many other ways. commissioning. Demand flexibility is, is a little bit more complex. So although energy efficiency is clearly a reduction of kWh, demand flexibility can be a reduction or increase of kW at specific times. And you can see below a diagram of a load curve of a building in which there's a baseline in blue and an area that can be saved by curtailing energy. And this is a typical framework for demand response, where there's an emergency on the grid or some other grid need, and the building is required to reduce the load, and the building can drop it and can provide this flexibility at specific time of the day, specific day of the year, so it's time dependent. So is demand response the same of demand flexibility? Well, let's think about this. Demand response is typically motivated by hot summer afternoon grid peaks. It's short duration. There's a few events per year, and it typically requires a reduction of load. You can see on the right, kind of the same diagram as before. The gray area is the demand response window, and you can see that what the building does is drops the load. On the bottom graph, you can see the demand compared to the baseline. So you basically virtually generate that energy, because if you had not done this action, the building would have consumed much more, which is the line with the dot in light gray. So basically, you're giving back to the grid some energy, providing some flexibility. And this is really a traditional way of doing demand response. At the bottom, you can see sort of a load duration curve that substantially describe the number of hours that the grid sort of uses a certain amount of power. And you can clearly see that there's a high peak on the left, which means that you need power plants to provide that power for a very small fraction of time, possibly a few hours per year. So demand response is basically a solution to provide that flexibility without building generation infrastructure. Okay, so what's new? There's new drivers and motivation, and this has been discussed multiple times during these days. There's urgency to decarbonize buildings and the grid. There's new variable energy resources being deployed, electrification, which increases peaks at a specific time of the day. There's need to modernize the infrastructure and expand access. So this is really changing the way we think about energy use in buildings, and demand flexibility has to cover all these needs. There's also new location-specific grid needs. Many of you, and this has been discussed already several times yesterday and today, this is the duck curve, which is basically describing the profile of the grid in California with increased penetration of solar. And you can see that has the shape of a duck. So this is obviously problematic for the grid, because they have to cover the high ramp, and sometimes you have energy being thrown away, renewable energy thrown away, because it can't be used, and you have to curtail renewables. But it's getting kind of interesting, because there's other animals. This is a very funny NBI picture that shows different places in the US where they have different shapes. So there's a alligator shape, there's an armadillo shape in Texas, and another one in Hawaii. So really, this is becoming a local issue, and the response to this issue in buildings have to be related and aware of what's needed by the local grid. There's also kind of different ways that we want to provide flexibility. I listed here efficiency, which is basically a reduction throughout the year of the energy use, but you can also think about load shed, which is the traditional demand response. Also load shift, which is a major interest in many states, including California, kind of shifting the load from one period to another. And also modulate, which is like high frequency sub-second or second time scale response to provide voltage or other type of services to the grid. So what are the technologies that can deliver GAP? Are they here? So is GAP real or not? And this is a complicated answer because the technology is mostly here, but to make it the system, which is controls and technology, work together and work in a way that can provide flexibility, makes this technology kind of in a spectrum of availability. There's products that are already commercially available. Smart thermostats are an example, heat pump, water heaters. There's other systems that are pilots, so heat pumps, you see them there because the product heat pump is already a product, but the way of making it flexible is not really kind of supported by most manufacturers right now. And you have a spectrum of technologies that I'm going to describe a little bit in detail in the next few slides, especially two examples. You can see the national roadmap for GAB that LBNL authored, and Marianne already went over that. So one important I would say new technology, although it's 30 years old, but it hasn't been adopted that much, is thermal storage. In particular, behind the meter thermal storage. There's an initiative by the Department of Energy called Store for Build, led by 4 national labs, including LBNL, that is looking at material development, component integration, and system integration to generate the new kind of market transformation and really develop products that can be used to shift energy. Although buildings have already mass that they can use passively, dedicated thermal storage is a new and great opportunity to provide flexibility and support the integration of heat pumps and other technologies. The way we really think about this is like a sequence. We develop materials. These materials go and get integrated into TES, which is thermal energy storage devices, and those get integrated into systems. And the systems could be either factory integrated, so like package units, like a heat pump water heater is a package system, has embedded storage, and so that's one of those. Field integrated, you could think about a heat pump where you connect a storage system in the field, or custom design. And these are large systems, for example, campus water tanks or other larger scale systems. So LBNL and the other labs are working on kind of these steps to advance the technology, adding controls, and looking at different building segments and, as you can see at the bottom, end uses. And an example of this, I'm not going to go into details of all the project. There are several of them. They're currently being run. But an example of this, which I think it covers also heat pumps, and it's pretty interesting, is the use of PCM, which is phase change material, thermal storage. It could be both on the hot side or on the cold side, integrated with the air-to-water heat pump that you can see there to provide space conditioning and water heating in a home. And this is a system that we designed and developed at Berkeley Lab, and it was recently deployed in a house in the Northeast to show that it also works in cold climate. And since this is very exciting technology because the storage is compact, so you don't need a huge tank for this. At the same time, storage allows you to downsize your heat pump because you can kind of shave the peak, and you don't need to design the heat pump to cover those, like, 2% of the days in which you have, high peak. If you coordinate well your storage with your heat pump use, you can use the storage to supplement the heat pump, and then you can downsize the system. So really a system approach here is what's winning. What Peter was mentioning a few days ago. This is a system that is, for residential or light commercial systems. Larger systems are even more complex. And talking about coordination of systems, an essential piece of GEP is really controls. And we heard that from Marianne and other speakers before. Controls really need to go to the next level to be able to change the load of the building. And this is sort of kind of everybody, I think in this call knows, but systems that have HVAC systems do not control based on the energy use. They control based on the variables that need to be controlled, like temperatures or flows or pressures, but they don't take their energy use into account in the control logic. And so what needs to be done now, because we want to modulate the energy use, is find a system that understands the impact of the control sequence on the power use to then be used to modulate it. And our approach is really looking at kind of segmenting the market that goes from small residential and light commercial systems that we can package and we can kind of develop a control for that is pretty canned and generalizable. Larger system like district heating system like George Moore Jones presented yesterday, where you can have a custom approach to optimization and flexibility, where you can, if you need an engineer to design that, it's viable in terms of economics. And then in the middle, there's like the hard buildings. They are like the large buildings. They have built up system that are not large enough to justify a lot of engineering, but they're not all the same, like in the small package systems, then they're harder to optimize. What we have been working on for several years, and if you see the older institutes, there's some discussion of that. What's here on the right discussed as MPC, Model Predictive Control, is an optimization approach that takes in all the information, including weather forecast, prices, and uses that to produce a schedule of set points, in this case, as a supervisory control sequence that gets pushed into the control system. In this case, could be a thermostat or it could be a building automation systems. And that produces, as you can see below, both a service that is adequate to the user, so the user doesn't complain and doesn't get upset, and at the same time changes the load shape, as you can see. So this is kind of the next generation of controls that LBNL is developing. And the key aspect that I want to sort of make sure to address here is that these systems have a long history, but they still have barriers to adoptions and scalability because of lack of interoperability. And many of you are already familiar with that. If you have to integrate BAS, other systems, another BAS of another vendor, other meters, cloud controllers, and everything else, you need to kind of do it manually. On the right here, you can see a military base that has 27 buildings and 27 workstations, one for each building with the different automation systems. They don't talk to each other. It's just like nuts. So how do you go about implementing this? And I know that there's a lot of people who do training on building automation systems. And I think this is a key question for the future. Are you gonna implement this sequence in the BAS to create flexibility through, this is a Tritium system with a wire sheet. You have to figure that out into that system. It's one-off. Or are you gonna try and generalize it? And this is really like where the R&D goes in LBNL's effort, is like, how do we generalize and how do we try to create interoperable systems that are scalable? Just a quick example here of a project that we run. We develop advanced controls for those like smaller, more uniform and consistent systems. We developed it in a model, we run it in the model, then we run it in FlexLab, which is a laboratory flexible facility we have at LBNL. And then we run the same algorithm, porting it into two sites, one in New York and one at UC Davis, with minimal changes of code. So this is really like our exploration of how these things can be scaled up, as opposed to doing a single project that is different every time. And we hope to kind of use the same logic and the same approach for those complicated buildings in the middle that are, more complex and built up. So revise conclusion. Are grid interactive efficient buildings a reality? Yes, but not at scale yet. And they're coming. And so you're going to see in the next two presentations example of that. I want to close with key takeaways. If you have like 1 minute to look at this one. CAB is basically energy efficiency plus demand flexibility. We have done energy efficiency for years. Demand response is a type of demand flexibility. Demand flexibility requires strategies beyond demand response. This can be continuous, like price response. Technologies are commercially available, but there's also other that are being developed, like thermal storage, and some mix of them, and some that are like earlier stages of development. Scaling will require addressing several technical issues like interoperability, but also non-technical barriers. One of those is workforce training, and because the community here is really looking into that, my question to you is, what are you doing to make sure that these new innovations that are coming out the pipe, they're going to be in the next curriculum for the next generation of students and technicians and engineers in the field. With that said, I am going to close and take questions.
Hi, Marco. There's one question in the chat. It says, I heard recently that VPP is a replacement term for DR. Would you comment on this?
Yeah, VPP is virtual power plant. It's a sort of term that means whatever you want it to mean. It is basically aggregation of systems of local or single buildings that then get used to be bidded into the market or used for a larger scale for the grid. So it is an aggregation technique, and it is not directly a replacement for DR, but it's like a version of DR that works at scale.